My name is Sriram Vamsi. I'm a senior software engineer at Walmart. So today we'll be exploring a topic for Airflow called as exploring DAG design patterns. We'll cover different ways of creating DAGs, how to optimize them and make them more efficient from the ground up to advanced patterns. Advanced patterns. So we'll start with the motivation. We'll start with the basic introduction to DAGs in Airflow, some of the best practices for tasks itself. Then we move to organizing our tasks. How then we get to the DAGs where we can make our DAGs more flexible, parameterizing these DAGs. And lastly, we'll touch a little bit on parallelism and how to efficiently exploit parallelism in Airflow to make our the DAGs more performant. Starting with the motivation, making our DAGs more efficient and performant will reduce the maintainability of the DAGs essentially. So we can use a single DAG for running multiple workflows and jobs. The DAGs can scale more efficiently. That way we don't have to deal with issues more often. Using efficient patterns can also reduce the cost of running the DAG. We can also improve the performance of the DAG by running some of the components parallelly. We can achieve higher SLAs on our DAGs. We also have the flexibility to reuse a single DAG for different operations. Now let's explore. So coming to the basics of a DAG, to introduce a DAG has several key components. One of them is tasks. We can see the tasks highlighted in the boxes. And then the task can consist of two different things. One is operators, or operators can be like a shell operator, bash operator. We can also have sensors within the tasks. And then the next important components are the connections or the dependencies within the DAG. So these are the two main components, and organizing these two would be the focus of our presentation. So let's start with some of the best practices for tasks. We should keep our tasks small and focused. Overloading a task can create a lot of problems essentially. So in this case, let's say we are doing too many things. One is extracting the data, cleaning up, transforming data, loading data, and everything in a single task. So if the task were to fail, you would have to redo the operation every time. So breaking this up into 3 individual or 4 individual tasks will help us in making this more efficient. So we should clearly define our focus for a given task. Let's look at the idempotency. The task can be expected to fail any number of times, or can fail in between while we run. So we should design our tasks in such a way that the tasks are idempotent. Even if the task were to run multiple times, we should expect the same result. So in this case, we are trying to insert a record into a database. If we use a regular insert, we'll be inserting the record multiple times. So an upsert would check if the record already exists, and then would only insert if the record is absent. That way, even if we have to rerun the task multiple times, we would achieve the same result. We should also treat tasks like a transaction. Essentially, if given that we expect the task to run like multiple times, we should not have any side effects. We should treat the task like a transaction. If we were to fail in between a task, we should also clean up so that there are no side effects. That way, when we run next time, we have a clean all or nothing kind of situation when we run the task. Yeah, other important thing is, given the tasks run in a distributed environment, there are databases involved, multiple clouds are involved. We may be talking to different systems. We expect, as we are talking, we expect the task to fail. Having retries to the task and error handling the task is really important. So that way we don't have to deal with intermittent errors and failures. So choosing our retries and retry time window is really important for improving the overall reliability of our DAG. Let's look at an example of DAG, a good versus a bad DAG. So on the left, we have like a bad design of a DAG. So if you look at, we have like a ETL job, and then we are doing some data quality check. Then we are generating and emailing a report on the left actually. So some of the main problems with this DAG is, as we can see, the ETL operation is always being done in a giant task. We'll have reliability issues with this. So on the right, we can see that the same thing has been broken down into 3 independent extract, transform, and load. We have broken this into smaller focused tasks. And then we have added some retries. So when we are extracting data from an API, we expect the data to kind of to fail in some sense, essentially. So we added this retry mechanism to make sure that the extraction happens reliably. And then later, as we can see, we are also adding logging to each of the different tasks so that we log all the errors properly. Next, we can see that we have also moved the data quality check earlier in the flow. So this would allow us to make sure that we fail early if the data quality were to check and then not execute the load operation. So that way, breaking this down and adding the data quality check earlier, adding logging, adding retry mechanism is improving our performance of our DAG significantly. Next, we'll see look at different ways of organizing our tasks within a DAG. So one of the first things which I would like to focus on before we move to the organization is trigger rules. So trigger rules are really important in Airflow. Trigger rules are typically defined on a downstream DAG, which has a dependency on a couple of upstream, defined on a downstream task, which have dependency on upstream tasks. So in this case, we have task A, B, and C. Task B has dependency on task A and C. So we have to define how and when the task B executes actually. So there can be multiple scenarios in which task A and task A can succeed, task C can succeed, both can fail, or either of them can fail. So in order to achieve the correct behavior, we need to make sure that the correct behavior is defined on task B when the task B should run. So some of the trigger rules are like all done, one failed, all failed, and all success. So these are like illustrated in the diagram. So now let's look at the couple of ways of organizing our tasks. So one of the first patterns and the clean and neat pattern is the linear workflow pattern, where we have like a linear flow of tasks. Where in the right, we can see that there is extract, clean, transform, load, and validate. We have a linear chain of flow, a very simple, very simple DAG. This can be helpful for like many use cases. But one of the major limitation of this particular workflow pattern is that there is no parallelism within the DAG. To add parallelism to the DAG, let's say we want to do like the data preparation stage parallelly. We can, one of the things which we can do is we can run the processing in parallelly. In this case, unlike the linear DAG, we are having 3 processes, process A, B, and C, run parallelly to run the data preparation job and then aggregate the results. This way, we can improve the performance of our preparation job and increase the throughput of our data pipeline. The next pattern we want to say is the branch and conditional execution. So this is a pattern in which we can add a conditional data quality check and then take different paths in the downstream. In the example, we can see that we are extracting some data. and then we are doing a data quality check. And then if it is good, we process the data. If it's bad, we kind of clean the data and load the data. So one of the things is we can add some basic logic and intelligence into the DAG, and have much more efficient processing of our pipeline with the simple branch operation. We can also like save costs, and then have the possibility of like alerting in case of a bad data quality, and multiple other options within the tag actually. So yeah, one of the cons of this is, as we're introducing the branch, if we introduce too many branches, it can easily add the complexity of the tag. We can end up with paths which are dead, which are like not being used in the DAG, and can increase complexity. So it's one thing to be aware of. This is another example of branch and conditional tag, where we check the type of the file, and then do the processing as necessary. So depending on the type of the file, we call the corresponding processor. We also have alerting mechanism built into the DAG itself. One of the important things to note when executing branch and conditional is to properly define the trigger rules on the downstream DAG, downstream task actually. So when should the downstream task run when it is dependent on a couple of upstream things? So in this case, when should the load database run? Should it run if we should, in this case, we have to make sure that if either process CSV or process JSON is successful, we can execute the downstream like load to database. There is another operator called another branch and conditional operator, which is like binary. The previous one was can have multiple possibilities. This is a binary operator where adding a simple check can kind of, in this case, we are checking if the data is available or not in a simple branch operator. And then if it's available, we process the data. If it's not available, we skip processing actually. So if we don't have this simple thing, we would have run the whole processing pipeline with no data. This would have been a bit costly. So adding a simple branch operator can take us a long way. Next, we look at something called as dynamic task generation. We previously looked at a fan-in and fan-out pattern, where we can do parallel processing of data in multiple parallel tasks. There, in the case of a fan-in and fan-out pattern, we have to statically define the number of parallel tasks that can run to process the data. One of the new features of Airflow is the dynamic task generation, where we can, based on the number of inputs, we can dynamically define the number of parallel tasks running within the DAG. This can be really helpful. For example, in this case, we have a DAG which is kind of processing the stores, departments, actually different stores. So we have store 1, store 2, and store n. We can define n different parallel processes to run this processing, then aggregate, and then continue the rest of the DAG. Dynamic DAG processing helps us in dynamically increasing our number of processors that can run to improve parallelism within the DAG. This is another example of a dynamic DAG generation example, where we have different, let's say we need to process different files. We don't know statically at compile time on the number of processors we need. So let's say we get the files from an API, or we want to look at an S3 bucket to get the list of files. Then we can use dynamic task generation to dynamically generate processors for each file, run parallelly, and then aggregate the results. The next thing I want to focus on is something called as task groups. This is another good way of organizing our task groups. Task group doesn't have doesn't bring any functionality on its own, like parallelism or any additional functionality to the DAG. It's a way of organizing our tasks within the DAG. In this case, we have 3 tasks which are like logically, which can be logically grouped. The ETL job, the ETL process can be logically grouped into a task group that can be executed, that can be seen as a block on the airflow actually. So we can, instead of passing the individual parameters and everything, we can treat the whole block of 3 tasks in this, the ETL job, as one thing. We can pass in the parameters, and then we can take the output from the task group directly instead of dealing with the individual tasks. This is one more example where we have a group of ETL jobs as well as load and validate tasks. What we can do is we can group them into different task groups, and then we can directly define the dependency, like the start, task group 1, task group 2, and end. And we can abstract out the task groups and task groups as they are like logically connected. That way we can isolate the that way we can we do not have to deal with the underlying components when we are defining dependencies. Even in the Airflow UI, this would show up as a single component. Each task group would show up as a single component. This is an example of some of the things which we have discussed. We'll have like a start, stack data. Now we need to transform data. One of the things which we can do is we can use dynamic tasks to dynamically generate a loading of different data sources. Then we can we have a reporting group which can be logically grouped into a task group. We have validate data, generate report, and send report as a reporting task group actually. So this is a way of demonstrating combining task groups, parallelism, dynamic tasks, and within the single example. Now that we have looked at, previously looked at how do we define tasks efficiently, how do we organize tasks with linear flow, fan in, fan out, dynamic tasks, task groups. Now let's look at, now that we have tasks and the dependencies clearly defined, let's look at how we can configure our DAGs to make them more efficient, reusable. So one of the first way is to leverage DAG parameters. So every DAG has a set of parameters that we can input. So by using these parameters, we can use the same DAG for passing different parameters to reuse the same DAG for different use cases. We should try to leverage this as much as possible. We should also, let's say, as much as possible, we should try to implement everything we need for a given data flow into a single DAG. Sometimes we may not be able to organize everything into a single DAG. We may have multiple DAGs. So in that case, instead of duplicating logic between 2 different DAGs, we can use Cross-DAG. How we can, there are different ways of having Cross-DAG dependencies. We'll look at some of them. And then there is also the concept of dynamically generating DAGs for complex workflows. So let's explore each of them in detail. Coming to DAG parameters, each DAG can have different parameters. The default parameters are like the start date, schedule, and other things. So there, we also have something called as params. We can pass in different values. These parameters are accessible within the DAG and within the DAG as well as tasks. So we can customize our DAG to use different parameters for different use cases for improving the reusability of the DAG. This is another simple example where we parameterize a DAG we have defined a category. We have like a processor DAG. We have defined a category parameter. Using this category parameter, we can pass in different departments to process the different DAG. To process the different departments using the same DAG, we can process electronics, clothing, and books as a parameter, and use the same DAG to to run these different processing across all these departments. Now let's look at the cross-DAG triggering. In this case, we have looked at a DAG A and DAG B, which are different. So one of the reasons in which we can have two different DAGs is a DAG can only run on one schedule. Let's say there are two components, one is ETL and then other is generating report. If you have to run ETL at one schedule and then generating the report at another schedule, then we would put these two in different tags for scheduling issues. Let's say we want to trigger the data processing. We want to trigger the generate report after data processing. Then we use a component called as trigger run operator, where we can define that when the data processing is complete, we can trigger the reporting process. There is another way of triggering or achieving the same functionality. Instead of explicitly triggering, we can also have like a sensor. This sensor can wait on a DAG or a task in another DAG. In this case, this example, we have task B, DAG B, and then DAG A. A task in DAG B is constantly waiting on DAG A to complete. This is a thing called as external task sensor. Can wait on a DAG or a task to complete before it kicks off execution or continuous execution. This way, we don't have to explicitly trigger the DAG A. Now let's look at the concept of dynamic DAG generation. This is a complex workflow where we generate DAGs dynamically for different configurations. This is not highly encouraged unless you are familiar with this mode actually. So let's say we want to have we should try to reuse our DAGs as much as possible instead of dynamically generating to add like this adds like a lot of complexity. But there are like very specific use cases for like dynamic DAG generation. We have configuration, and then we want to generate DAGs we want to generate like say, similar DAGs which needs to run at different schedules. Then the dynamic DAG generation is a good idea. One of the advantages is we can have a template for the DAG and generate multiple DAGs from the template using the help of a config. That way we can easily maintain the template instead of changing multiple DAGs at once. Let's look at example. In this case, let's say we want to generate DAGs. We want to have like a different DAGs for books, clothes, and electronics. We run at different schedules. We have defined that in the config. In the config, let's say we have a category for electronics, we have a category for clothing, category for books, and then we have a couple of parameters like schedule and an endpoint. Essentially, we have the same DAG. We want to run a different schedule with slightly different parameters. So in this case, dynamic DAG is a good use case where we can have a config and a script and a template to dynamically generate DAGs for the different use cases. Last but not least, let's look at example of DAG concurrency. So now we have looked at different ways of running tasks parallelly, improving parallelism, dynamic tasks, and different things. Actually, even after defining this, it's important to control the concurrency of our DAGs. So there are different ways of controlling the DAG concurrency, task concurrency, and there are also ways to rate limit the access to like resources like databases and all that. So two of the ways is like max active runs. Let's say we are running a DAG. We are doing a backfill. We want to have the same DAG run for like multiple dates. we can control the number of DAG runs currently active using the max active runs. In this case, we have two DAG runs running concurrently. The third one is in queue. We can also control across the DAGs. We can also control maximum number of active tasks. In this case, we can see 5 greens. These 5 greens indicate that across both the DAGs, we only have 5 tasks running. That way, we can limit the amount of resources and amount of tasks running parallelly. There are other parameters at the DAG level, scheduler level, and to control the concurrency. So it's important to be aware of these parameters to maximize the performance of our DAGs. That's it. Yeah. So in conclusion, we looked at some of the task best practices, looking at everything from idempotency, keeping a task focused, and then we looked at some of the ways of organizing our tasks, like direct linear flow pattern, fan-in, fan-out pattern, dynamic tasks, task groups. Next, we looked at a couple of ways of making our DAGs more flexible using DAG parameters, dynamic DAGs, how we can reuse our existing DAGs using cross-track triggering capabilities. Thank you.